Hello, everybody. So this is going to be a little bit different talk in Vladen. I'm not going to focus entirely on computing, but I'm going to talk today about how we at Boeing are putting quantum technology on the move. So if you have questions, go ahead and ask, and we'll get on those. So let me start. I know most of you know about Boeing. We like to say we're a 2007 or 107-year-old startup. And we like to keep that mentality in everything that we do. We are essentially a company that was formed out of the merger of many, many companies over the years. And we have several businesses, commercial airplanes, which hopefully everybody took and used a Boeing airplane to fly to this, except for Jasper. I'll give him permission to use one of his own. We have a defense, space, and security business, which works on, produces products for governments, satellites, etc. We have our global services business, which provides services to keep all of our other products working, and Boeing Capital Corporation, the hidden business that we have that actually helps people finance the procurement of airplanes because it turns out they're very expensive to buy. Underneath that, we have our engineering, tests, and technology team, and then our research areas of the company sit underneath there. I sit in an area called disruptive computing networks and sensors. Our job is to be an incubator for future technologies. We like to think that we are the deep tech incubation startup area, we're the startup area within the company. So we like to think of ourselves that way. So we have organized ourselves around a number of projects, and one of the things that you see right away is we're not focused on one area of quantum technology, but we have projects that span the breadth of quantum technology. We like to, one of the reasons we are doing this is we see multiple applications within the breadth of quantum technologies that align themselves with our business needs. And so we want to make sure that we're investigating those areas that have the best probability of lining up with those future business needs and are doing the research to understand how to convert those research activities into prototypes and into products that we can then insert into our current products and services. So I'm going to start today talking a little bit about our quantum computing applications team, and it's a very important emphasis that we're an applications team. We actually don't build quantum computers. We're in the process of understanding how do we use those quantum computers to solve our problems. So the problem I want to talk about today, we've been in the last 8 or 9 months, we've been starting to look into a quantum chemistry problem that's quite interesting and really relevant to challenges that we see on our products. And that is the paints, the coatings that sit on our airplanes are constantly exposed to ultraviolet light, but that ultraviolet light basically degrades the polymers. You can see in the middle there's a polymer that has a long name that I should have memorized, but I didn't, so you'll forgive me for that. But as UV light hits that polymer, it breaks some of these bonds, and in breaking those bonds forms another material called quinone methide, which that does not provide the UV protection that the coating is supposed to do. Allowing that UV light to then transition through to the underlying composite essentially degrades the performance of the composite. So what we want to do is figure out how to model and understand this photochemical reaction in such a way that we can figure out ways to design molecules that actually will perform their coating function but also better protect against UV exposure. These are really difficult to do model chemical processes because you not only have to model ground state behaviors, but you have to model excited state behaviors, and there are multiple channels. What we have managed to do is extend on active space selection methods to figure out how to do active state selection in situations where we have both ground and excited state ground and excited state molecules that need to be considered in the definition of those active states. These methods and models are, right now, we're working on things that are small enough to use classical methods and quantum methods so that we can compare them. And we're in the process of then figuring out how we allocate parts of a long calculation, how we allocate those to classical techniques and what we are going to accomplish via quantum methods. In the end, one of the things we note is that density functional theory, which is one method by which people try to calculate chemical molecular energies, we've seen large corrections to these terms, which basically have helped reinforce our expectation that the approximative methods of typical classical solutions are not going to be adequate to help us understand these processes. And so we're going to need more detailed methods, which is where we hope that these quantum computing applications will come in. So I'm going to now switch to talking about our Q-Node project, which is a project in the space of quantum networks. So Q-Node is a project with the goal to develop and understand all of the integrated photonic components that are needed to act as the integrated capability of a quantum repeater in an entanglement swapping network with memory. So it's a long-term goal and objective. This project is really then trying to understand the capabilities, needs, and requirements of the individual components, how those components need to be connected together, and how we can effectively assemble these things into a piece of hardware and use them in a potential entanglement swapping network. So to do this, we have taken the approach, and in fact, there's a really interesting philosophical discussion about how to approach going down and researching what you would need to do in an integrated system. Basically, there is a homogeneous materials approach. You try to do all your photonics work in the same photonics material system, or a heterogeneous integration approach. And many people in the research community are working on the heterogeneous integration approach, basically looking at it going, I don't have a material that has a good Chi2 or Chi3 nonlinearity, also has a spin photon interface, doesn't have a memory candidate transition within the material that I can get, doesn't have the ability to use it doesn't have all of these requirements, so I'm going to choose materials that address one of these requirements, and I'm going to use heterogeneous integration approaches that are used in the photonics industry to put all those different material systems together. We instead are focused on trying to down select to one material system that we believe answers most of these and eliminates what we see as the potential risk of all of those different interfaces between. We've settled on silicon carbide on insulator. The challenge that we have in silicon carbide on insulator is that the thin film of silicon carbide is not sufficiently uniform to build photonic components of high enough quality. So this has been our focus for the last 9 months, is trying to determine how do we fix this technical challenge in order to enable us to use this material system. So there are 2 areas of results that I want to show. One is on the right. Let me talk about that first. And this is our development of a novel method, a dopant selective wet etch using photoelectrochemical etching that allows us to do a drastic reduction in the wafer-wide total thickness variation. TTV there means total thickness variation. So it's measuring essentially what's the difference in thickness between the upper left corner and the lower right corner of that grid, which is about 1 square centimeter when you look at the dimensions of the plot. When you look at the bottom, we've actually reduced that variation from over 700 nanometers to roughly a little under 100 nanometers. Since this plot was taken, we've actually gotten a little bit better results than that even yet. And our goal now is to scale that to full wafer size. A 1 square centimeter region is interesting, but it's not. These are kind of typically 3 or 4 centimeter wafers. And so we're going to try to move to larger wafer scale and eventually to kind of 300 millimeter wafers. On the left, on the left of the slide, you see work that we've done to address all of the individual component needs to show that, yes, we believe and understand that we have the ability to do all of the different components in this same material system when we're able to get samples that are sufficiently good. So on the upper right or upper left, you see a plot there that is indicative of us embedding single color centers in the silicon carbide material in optical waveguides, so that the emission of those color centers is picked up on the waveguide and done direct detection of the light output coupled through that waveguide. This is useful because in the end, if we want to have an on-chip quantum memory that is used for this repeater, we're going to have to be able to interact with that through that waveguide. We're going to have to collect that single photon that comes out of there and use it. In the lower left, you see a picture of an SNSPD. That's a superconducting nanowire single photon detector that is laid on top of a silicon carbide waveguide. This allows us to do single photon or photon counting of photons that are passing through that photonic waveguide that's laid down on that silicon carbide material. You see a grating coupler there that allows us to couple light into and out of said waveguides, and directional couplers, things that we can use to create essentially beam splitters or for things such as a Bell state measurement. So we've done the engineering work to understand that we can deposit and produce color centers where we want them. We can do those in such a way that they're captured in a waveguide, which we've engineered. We've shown that we can incorporate and build and integrate detectors in with those waveguide materials and other components that are needed. And provided we solve the thickness variation, we then feel like we have a good path forward to an integrated photonics platform that allows us to capture most of the functionality needed for a future repeater for networks. Very excited about this work. Let me move on. It's not enough for us to look at network devices. The other thing we actually wanted to do is understand how we might use these networks. So to that end, we've been working with our colleagues at HRL and at the University of Illinois Urbana-Champaign. We have developed a protocol that secures control plane nodes of essentially a hybrid quantum classical network. So think of this as a regular communications network where we've added the ability to produce quantum resources at certain of the nodes on that network. So the ability to produce single photons on demand, or at least in a reliably enough method that they can be used as a resource on that network. Those quantum capable nodes can use something called the quantum position verification algorithm. And we've developed an augmentation to this algorithm that allows us to produce certain guarantees about the quantum capable nodes that we believe augment the security, the overall security of the network. In effect, allow us to make guarantees about those specifically, essentially those nodes that as you see in that upper right figure, that red node with a P on it, we're basically running that algorithm. We're able to make guarantees about that node P that then we're able to use in order to understand the security posture of that node. One of the things that this can be done is can prevent a typical network attack that's called the Border Gateway Protocol hijack, wherein one network node essentially poses as another node and redirects all of its traffic through there. This is typically used for things like denial of service attacks or other network attacks. We're very excited, and we'll be continuing this activity over the next year. So now I'm going to switch to talking about our progress that we've made in the quantum sensing domain, which is one that we, again, feel very confident about. And so before doing that, I want to really talk about how navigation is really. We hear a lot in the quantum technology space about how quantum navigation is going to fix the navigation problem. What I'm here to tell you is that the story is a little bit more nuanced and a little bit more subtle than this. And so the better way to think about navigation and how a sensor is able to help navigate a platform like an airplane is that really you have to blend multiple strategies because each of these strategies produces a set of errors that as those errors accumulate, they reduce your certainty about your overall position, and in so doing, degrade your understanding of where you are. And the goal here is to blend sensors that have different error accumulation mechanisms so that you are complementing so for instance, if you are looking at an inertial sensor, that inertial sensor measures velocity, acceleration, and rotation. Its error characteristics grow with time. I want to augment that with some other error mechanism that doesn't grow with time, but maybe is different from location to location, or one that is uniform every time I measure it. That's essentially what GPS does in an integrated GPS inertial system. That GPS system is doing ranging to fixed points, and so its error characteristics essentially every time you make a measurement, you effectively get the same error. Combining those two things allows you to make a much better estimate of where you are and really provides you with the best solution. The challenge becomes, in the end, that not every type of measurement is always available. And if not every type of measurement is always available, how do you respond to the removal of one of these? What do you need to do overall as a system to make it more robust? It becomes one of how do you balance all of these things together and blend them together. So anyone who comes in and tells you that one navigation solution is the answer is telling you a fairy tale that really is not consistent with reality. And you should immediately go to, well, okay, how are they simplifying the story in such a way to make their sensor look most promising and ignoring everything else that's needed to solve the problem in other situations. So that said, and I can get off my soapbox and talk about what we've been able to do. Our goal here is to really focus on the two areas that quantum sensing actually is able to respond. One is the development of inertial sensors, and the other is the development of quantum magnetometers that are used to do a map matching approach by measuring and correlating the measurements of the platform's measurement of the magnetic field with the local magnetic field that is produced due to the Earth's magnetic field plus all the magnetic fields that's produced by basically human activity on the ground. We've been working very closely with two partners. Aosense is our partner working on the quantum inertial measurement units. Sandbox AQ, who Nadia Carlson gave a talk earlier in the conference about their work on quantum magnetometers. We were very happy to work with these, and we ran ground and flight tests of these navigation sensors. We ran the world's first successful ground test of a full 6 degree of freedom inertial sensor. Nobody in the world has ever done that. We're proud to be the first to accomplish that, and we will be turning that ground test into a flight test early in 2024. Between the ground test and our first flight test, which occurred earlier this year, one of those inertial sensors had a problem with its oven, which basically its atomic source. And so we actually had to pull that out of the system and flew a subset of our inertial sensors and the magnetic field sensor. But in so doing, we were the first to ever fly a quantum inertial sensor on an airplane. And further, we were the first to ever combine and do a flight test of multiple quantum sensors on the same flight. We produced over 5 hours of flight test data, and we have, since that flight test, been working on how to use that flight test to improve the system so that when we go back and test them in 2024, that we will have even better results than we had prior. I highlight the data you see on the upper right. That oval is data from our ground test showing and comparing the quantum sensor with a GPS-aided IMU. And you can, I don't know about you, but I really can't see much of a difference there, which is really remarkable for a test that lasted almost half an hour. Typically in a system that you would have just an inertial sensor, in a half an hour, that system would show hundreds of meters of navigation error, and here we're showing almost none. So I see I've run out of time, but I want to leave you with one thing, which is I've told you about a smattering of the things that we do, but stay tuned on look at what we are doing and watch our feeds, and we will be having some announcements that come out in 2024 on other projects that we're doing that we feel very exciting in the quantum technology space. Thank you for your time.